Okay, good morning. We are going to continue with switch reluctance motor drive. In the last class, we had looked at stepper motor, and we also said that switch reluctance motor is an extension of variable reluctance stepper motor. And in variable reluctance stepper motor, what we said was that we can calculate step angle, that is at every step how much it is going to move, that is by 360 degrees divided by rotor poles. How many rotor poles are there? Minus 360 degree divided by stator poles. So this is generally the way the step angle is calculated. And in switch reluctance motor drive, what normally we see is it is used for continuous rotation, because of which we will need rotor position information so that we would be able to fire the appropriate phase such that positive torque is developed. So let us say I'm going to have a power supply like this, and let's say I have a switch like this for one of the phases, and this is the phase winding. We are talking about A and A dash as the phase winding. Maybe we are going to have one more phase. Maybe it is a 6x4 switch reluctance motor. So we are going to have A dash, B dash, and C dash as three phase windings. So this is the third phase, C dash. And we are looking at a freewheeling diode that is coming along with each of the phases, so that when you switch off, let's say SA, if the current is still left over in A and A dash because it has an inductance, there should be a freewheeling diode which is allowing the current to freewheel through the diode, and you're going to have the current essentially flowing like this. This is the freewheeling path for A dash. Similarly, I'm going to have a freewheeling diode corresponding to B phase and a freewheeling diode corresponding to C phase as well. Let me call this as DB, and let me call this as DC, and this is going to be SB, and this is going to be SC, and this is the voltage that we are applying to any of the phase windings when we are turning on either SA or SB or SC. So assuming that we are having the structure of the SRM somewhat like this, let me draw this again, whatever I had drawn earlier. So I'm going to have maybe two poles here like this, and two more poles here. If I am talking about 6x4 SRM, so I'm going to have two more poles here, and similarly one pole here and one pole here. And we are essentially looking at the stator poles somewhat placed like this. And I'm going to have rotor pole, which probably I'm going to look at a rotor pole somewhat like this. So let us say this is one pole, and this is the second pole. This is the third pole, and this is the fourth pole. So this is the structure of the rotor pole. Okay. So let me call this as say A and A dash. And let me call this as B and B dash, and these are C and C dash, and let me call this as 1 and 1 dash, and this is going to be 2 and 2 dash. So right now what is being shown is the inductance or the poles are misaligned. One is neither aligned with C dash nor aligned with A. Similarly, this is also not completely aligned, due to which if I am actually exciting A and A dash now, it will try to move quickly towards A and A dash, depending upon whether 1 and 1 dash is closer or 2 and 2 dash is closer. So if 1 and 1 dash is closer, this is going to move in this direction. Basically, it is going to move in clockwise direction. So if I write the equation, electrical voltage equation as per Kirchhoff's voltage law, I should write VDC equal to I of A phase right now, whatever is the A phase winding current multiplied by the resistance of A phase winding plus whatever is d of Li divided by dt. Normally we write L di by dt, but here because the pole itself is moving, one is going to move towards A and A dash, we are going to see that they are actually going to the 1 and 1 dash, it is going to align itself with A and A dash, due to which you are going to have the inductance slowly changing. Inductance of A phase, if I try to look at it, it depends upon how much is the magnetic field lines that are flowing. So if it is exactly aligned, if I'm going to have A here and 1 here, whatever are the magnetic field lines that are coming, all those magnetic field lines will go like this, and it will go through the stator core. If I may call this a stator core, it will go through that, and it is going to again return through, let us say, I'm going to have this as A dash and this as 1 dash. So I am essentially writing this particular thing as A and this particular thing as A dash, and I'm going to call this as 1 and this as 1 dash. So I'm going to have essentially the magnetic field lines flowing like this, and then it will have to return through this and then complete the path. So if it is completely aligned, I will have more number of magnetic field lines created for the same current. If it is not aligned, because air is supposed to be a bad conductor of magnetism, I will not have as many lines produced. So reluctance of air is higher than for iron. So the reluctance is going to be much higher. So inductance is going to be lower. So whenever you are going to have, in general, I can say when the poles are misaligned, reluctance is higher and inductance is lower. Whereas when we are going to have the poles are aligned, we are going to have reluctance to be lower and inductance is going to be higher. This is the way your machine is going to behave. Okay. So we can say in general, whether it is variable reluctance stepper motor, that is the reason you are naming the motor itself is called variable reluctance stepper motor, because reluctance keeps on changing. So that is the reason we are writing d of Li by dt. So inductance is also variable here and current may be variable. Depending upon the inductance, the current will keep on changing. So I can write this as IR plus L di divided by dt plus I dl divided by dt. Rather than writing this as dl by dt, I can write this as dl divided by d theta multiplied by d theta by dt, which is actually omega. Whatever is d theta by dt is rate of change of rotor position. That is going to be whatever is the speed, omega m. So we can say the DC voltage applied is balanced by mainly three components. One component is IR drop, resistance drop. The other one is whatever is the rate of change of magnetic flux. So the magnetic flux, what it is changing, the magnetic field energy or flux. So I can say magnetic field energy change. That is essentially d by dt of half Li square. That is what is magnetic field energy or inductance stored energy. This is what is magnetic field energy change. So this can be written as half I square dl divided by dt plus I can say the other one is half 2I di divided by dt multiplied by L. So I can write this as this 2 and this 2 will get cancelled. So I can say Li di divided by dt plus half I square dl divided by d theta multiplied by omega m. Because I can again write dl divided by dt equal to dl divided by d theta multiplied by d theta divided by dt. D theta by dt we already called that as omega m. So I have put that omega m here. So when I talk about what is the power input to my SRM drive, I can say VDC multiplied by I. So I can write VDC multiplied by I is the power input to the SRM phase finding. If I try to look at one phase at a time, this is what is the power input. So that we can write from this equation. We had already written VDC is this. So I can simply write this as I square R plus Li di divided by dt. I'm just multiplying this equation by I. That's all I'm doing. And the next one is going to be I square multiplied by dl divided by d theta multiplied by omega m. Now compare this equation, whatever we have got, with what we wrote here. That is, magnetic field energy change is going to be Li di by dt half I square dl by d theta times omega m. So the power input actually is manifested in three forms. One is resistance loss. The second is going to be change in inductance stored energy or magnetic energy. What is the change in magnetic energy? The third is going to be, you are going to see a movement which is actually the mechanical power. Otherwise, how can the machine move? The machine is moving because the electrical power what you have supplied is manifesting itself in the form of mechanical energy conversion. So electrical to mechanical power conversion. So resistance loss is I square R. Whereas if you look at change in magnetic field energy, it is Li di by dt plus half I square dl by d theta times omega m. So if you look at it, this L di by dt and this L di by dt, they cancel out with each other. Whereas there is one half I square dl by d theta times omega m that is left over. So I can write this as, this is again resistance loss. This is again change in magnetic field energy. And what is left over from this is only half I square dl divided by d theta times omega m. So mechanical power is actually the conversion from electrical to mechanical power. What is happening during this particular situation, that corresponds to half I square dl divided by d theta multiplied by omega m. So we are going to have the power, mechanical power, which is going to be probably electromagnetic torque generated by the machine multiplied by omega m, that is half I square dl divided by d theta multiplied by omega m. Now, you can say that if I cancel out these two omega m here, the electromagnetic torque is dependent upon two factors. One is current magnitude. The second one is rate of change of inductance. If the inductance dl by d theta, the rate of change of inductance, if it is increasing with theta, I will have motoring torque. If dl by d theta is negative, I will have generating torque or reverse torque, negative torque. So it is very, very important to ensure that only when dl by d theta is positive, we should actually have the current to be, existent. It should be non-zero. I should not be zero. Or I should say I should be non-zero. That means that particular phase has to be conducting only when its inductance is in the increasing trend. Whereas if dl by d theta is negative and if I is pumped through a phase or I is passed through that phase, then we are going to have essentially torque what is generated that will be negative. So that is not really good for the motor. We already said this in the last class. This will be detrimental to the motoring operation of the machine. So in this particular case, this expression very clearly says that the direction of current does not matter as far as the switch reluctance motor is concerned, even variable reluctance stepper motor is concerned. The torque cannot be reversed only by reversing the direction of current. Rather, only it can be reversed if we are firing a particular phase when dl by d theta is negative. If we want positive torque, we have to ensure that that particular phase is fired only when dl by d theta is positive. So if I am looking at again this kind of 6 by 4 SRM, 6 by 4 switch reluctance machine, and if I am trying to draw the inductance corresponding to A phase, okay, so I have to draw it as though, because there are 4 rotor poles, each of the rotor pole, whenever it comes closer to, let us say, A phase, you are going to have maximum inductance. Whenever it is moving away, either in clockwise direction or anti-clockwise direction, either way, you are going to see that the inductance keeps on decreasing. So if I try to draw A phase inductance, I should draw it as though, let us say, this is 90 degrees and this is 180 degrees. And this is going to be probably 270 degrees. So this is theta. So if we say that when it is completely aligned under this condition, when the rotor is under this situation, theta equal to 0 degree. Let us say that is what is theta equal to 0 degree. That is where probably the rotor is exactly 1 and 1 dash are aligned with A and A dash. Under that condition, probably I'm going to have the maximum inductance manifested by A phase winding. So what is going to happen is it will actually come down within maybe exactly half the cycle. So if I say this is 45 degrees and this is going to be 135 degrees and this is going to be 180 plus 45 to 25 degrees. Okay. So I will have actually the inductance coming down from maximum condition to minimum condition. So it will probably come down somewhat like this. And then it is going to have a minimum value persisting for some time, and it will reach the maximum value once again exactly at 90 degrees, because it is going to repeat itself exactly every 90 degrees, because there are 4 poles in the rotor. So whatever happens from 0 to 90 will again repeat itself from 90 to 180 and so on. So I will have essentially something like this, and again it will persist like this, and at 180 degrees it will become maximum, and again it will come down like this here, and then it will probably be like this and so on. This is the way we are going to have the inductance profile corresponding to A phase. So this is L minimum. And if you look at B phase is shifted between A and B. If I look at the angle, this will be 60 degrees, assuming that it is uniformly distributed. Between B and C, again the angle will be 60 degrees and so on. So LA, LB and LC will be staggered from each other by 60 degrees. So let me again mention the angle here. So this is 45. So I'm going to divide this into 3 portions. So this is 15 degree each. This will also be 15 degree each. This will also be 15 degree each. So I'm just dividing the 45 degrees into 3 portions clearly. Okay. So this is the way it is. So let us say this is 15, this is 30, this is 45, this is going to be 60. So if I try to draw exactly how LB will be, LB will start like this, and within this is like 15, 30, so almost 30 or 45 degrees it is coming down. So I should say, let me write the angles clearly. So this is 75, this is 90. 90 plus 15, that is 105. 105 plus 15, that is 120 degrees. So from 60, within 105, it will come down. So I should show it as though it is coming down like this, and it is going to persist like this for some time. 105 plus again 45 degrees. So 105 plus 45 will be about 150 degrees. So this is 150. So by 150, it should have reached almost the peak. So it would have reached the peak here. Then it would come down like this, and then it will persist in minimum like this, and then it will go up like this and so on. This is the way it is going to be. So I should again show it as though it is coming down within 45 degrees. So 60, 45 means it is going to be around 15 degrees, and it is going to go around like this. So this is LA, whereas this is going to be LB. And LC will be again staggered from LB by another 60 degrees. So if I say LA, LA is here and LB is here, which is actually becoming maximum at this point. So LC has to be 60 degrees staggered from here. So let's see. This is actually one. This is actually 150 degrees, and this is 150 plus 15, 165 degrees. So if I say LB maximum is around 60 degrees, LC maximum should be around 120 degrees. So this is how LC maximum should be. So it will have something like this coming down, and there it will be persisting like this. And then I should have LC going on something like this. This is how it will be. And I should draw on the other side something like this, and it is going to have some zero interval like this, and again this is somewhat like this. This will be LC. So you will have LA, LB and LC somewhat like this with respect to theta. So if I really want positive torque to develop, I should have basically LA. Whenever I have dl by d theta to be positive, I should have this as the current. This should be IA. What I want as IA should be here, and then again IA should be here during this portion, and so on. So I should have IA pumped in only when dl by d theta is positive. This is how IA should be. So this is for positive torque production. Whenever dl by d theta is positive, I should be able to pump the current. So I should essentially know where the rotor position is, and correspondingly I should be able to. So I should have L versus theta profile stored as a lookup table for all the three phases. If I have got this, I should look up what my theta is. From theta, I should be able to say whether my inductance is in the increasing direction or decreasing direction as far as A phase, B phase, and C phases are concerned. So similarly, if I try to draw where IB should be, so I should say my IB should be, pumped in during this portion. So I should have IB during this portion, again IB during this portion, and I should have IB during this portion. So this should be the current profile, what I should be expecting. But you will not see the current abruptly rising like this. You cannot expect the current to rise abruptly like this. So what will happen is when you are trying to actually pump the current, although you should be probably pumping the current from 45 degrees and it should go on until 90 degrees. So you should have IA current from 45 degrees to 90 degrees approximately. That is when you have to have the current. But you cannot expect the current to abruptly rise at 45 degrees. And you cannot expect the current to abruptly come down at 90 degrees. So you will allow the current to probably rise even slightly earlier. So the current is going to rise. And if you allow it to rise, it will go to extremely large values because the resistance of the winding is small. So what you would try to do is just to limit the current to safe values. You will turn on and turn off the device. So if I am talking about SA being turned on, whenever SA is turned on, because it is connected to the positive of the device, you are going to see that the current increases through A and A dash. Once you are turning off this SA, you are going to have freewheeling taking place. The energy stored in this particular winding A and A dash, that is going to kind of expend itself. The energy stored is going to expend itself, so the current will come down. So that is what you see here. The current can increase, decrease, depending upon how long you are keeping the switch on. So whenever the current is increasing, it is SA on. Whereas whenever the current is decreasing, that is DA on. The diode is on. So you are going to see that happening. And at The end, when you want the current to completely expend itself, you will switch off SA, and after that the current should automatically come down. But it is not going to come down right away. Depending upon the time constant of A phase winding, it might take a while. The same thing happens during the next cycle also. You are going to allow it to come down. The next cycle also the same thing happens. So this on and off control is called current chopping mode or current control mode. So you will try to hold the current at a particular value and you will allow it to kind of go on and off, and then it will just oscillate between a maximum value of current and a minimum value of current, and the average will be corresponding to whatever is the current I want to really pass through a phase winding. So this is generally known as current control mode. If the machine is running very fast, if the speed is higher, so current chopping takes place whenever we are looking at slow speed operation of the SRM. Whereas when you talk about high speed operation of the SRM, under such a condition, the current might increase so quickly. So you might see that it is just rising to a very high value very quickly. So you may not even have the time to control the current at a steady value. And the moment it reaches almost the end of the inductance increasing region around 90 degrees, you will switch it off and then it will come down. So you might see that the current increases and decreases. And when the current is increasing, the inductance is also increasing. So you might see actually not a single slope. You might see initially it is rising quite steeply, then it rises very slowly, and then it comes down. So this is essentially the current profile you might see when you are looking at high speed operation. So you will see the current as a single pulse. So this is generally known as single pulse mode. So you may have two specific modes of operation as far as the SRM drive is concerned. It can be current chopping mode under low speed operation or current control mode. And for high speed operation, you might see single pulse mode. This will correspond to low value of L, whereas this may correspond to high value of L. So this shows a steep increase. This is going to be a steep increase in the current, whereas this is going to be a slow increase in the current. It will not be very quick in terms of increase in the current. So this will be a slow increase in the current. So these are specifically two modes of operation as far as the SRM is concerned. So when we design the control loop for the SRM, normally what we try to do is to run at a particular speed. So I may like to run the machine at a particular speed, which I call as omega m, mechanical speed reference. And I will actually sense the actual speed. How we sense the actual speed is a matter of detail. We'll worry about it a little later. So this is the actual speed. Now these two are compared and the error is given to a speed controller. The speed controller can be a PI controller, it can be a fuzzy logic controller, it can be any kind of controller that we want to design. So this is going to be error in mechanical speed. Now the speed controller decides what is going to be the torque that needs to be produced so that the gap in the speed, the error in the speed is bridged. because normally we are going to write this mechanical equation J d omega m divided by dt. This is actually the rate of change of speed that is going to be equal to Te minus TL, whatever is the electromagnetic torque produced by the motor and what is the load torque demand. So if there is something left over compared to the torque produced minus the load torque demand, the rest of it is going to go towards accelerating the motor. So this is very similar to what we see in a linear system, F equal to ma. M is the mass and A is the acceleration, F is the force. A similar thing is seen here. J is the moment of inertia of the rotating system, and d omega m by dt is the angular acceleration, and Te is the electromagnetic torque produced, and L is the load torque. So F equal to ma. This is exactly similar to, for a rotational system, it is J d omega m by dt equal to Te minus TL. Now, this is going to decide how much is the electromagnetic torque I require, so that required acceleration is incorporated into the system. So I have to subtract that from TL. Te minus TL gives me what is the kind of accelerating torque that is available. Now this decides indirectly how much should be the current. So this is whatever is the torque that needs to be produced, that is going to decide how much is the current calculation in a way. This is the current calculation. In fact, I should say this is not even Te, this is actually the accelerating torque. This should be the accelerating torque. So this has to be added to the load torque to get the total electromagnetic torque. So this electromagnetic torque has to decide how much is the current that needs to be pumped in through any phase. So this is going to give us what is I star, or let me write it in small itself, doesn't matter. So I can write this as I star. This is the reference current. Now, which phase has to conduct, that has to be decided basically by, so this is phase excitation or phase firing. That will be decided based on the rotor position information. So I'm going to have rotor position sensor. So the rotor position information may be, it can be a mechanical sensor, it can be the inductance versus theta. We said already L versus theta profile. This can be stored, and based on that, we are going to say rotor is occupying this particular position. So what comes out here is theta, and what comes out this side is also theta, and I'm going to have a d by dt, because differentiate that, then d theta by dt will be actually my speed, omega m actual. Now, which phase is fired, that is decided based on if it is a 6 by 4 SRM, any one of 4 phases may be fired. So this phase firing has to be decided based on this logic. So what I get here may be any one of the 3 phase currents. So this can be IA reference or IB reference or IC reference. And I have to essentially have a current controller. If the current is exceeding whatever is the safe value, that particular phase will be turned off. Otherwise, that particular phase will continue to conduct. So the current controller will decide whether I'm going to fire SA or fire SB or fire SC. It depends upon both the theta value, the rotor position value, and the current magnitude itself. So this is going to be the case as far as the SRM converter is concerned. So this is going to go to the converter. And SRM converter, I had already shown you how the SRM converter looks. So we said that it can have three phases being fired by three different devices, and there will be freewheeling diode. When the device is not fired, the freewheeling diode is going to take over, right? So this is the way it is going to be. Now, from the SRM converter, again, the three phases will be connected to the SRM motor, and we are going to sense the current from these three lines and feed it here. So this will be essentially IA, IB, and IC actual value. These are the actual values. These are the reference values. They'll be compared and the firing signals will be given to either A phase or B phase or C phase, depending upon the rotor position theta and magnitude of the current itself. Okay. Now this is coupled to a load. And SRM converter is going to have a DC supply. So this is going to be our VDC. Now, from SRM, we will either have L versus theta table, or we are going to directly mechanically sense the rotor position. So you can have a mechanical sensor. If mechanical sensor we don't want to use, then we can actually look at L versus theta table, and if we are able to infer what is the inductance value, then we should be able to say this is our theta and fire the phase appropriately. So mechanical sensor we can have, or we can infer what is the inductance, and then we can say this is what is theta and then fire the appropriate phase. Either way it can happen. So this is the overall control configuration for the SRM. Okay. So let us now try to probably work out couple of numerical examples for our stepper motor and SRM. So let me take the problem statement. The problem statement is as follows. At 10 by 8, that is 10 stator poles and 8 rotor poles, variable reluctance stepper motor is fed by, or excited by, rather than fed, let me say, is excited by a 1 kilohertz pulse for every phase. So if it is 10 pole in the stator, it will be A dash, B dash, C dash, D dash, and E dash. So that is what we call as 10 stator poles. So it will be corresponding to 5 phases in the stator. Okay. Now it is excited by 1 kilohertz pulse in every phase. Okay. Now determine the step angle. First question is step angle of this variable reluctance stepper motor. The second one is rotational speed assuming that no pulses missed during the rotation. And the third thing what is being asked is if the rotational speed needed is 12,000 RPM, what should be the frequency of pulses in each phase? So this is what is being asked. Now let us try to solve this problem. First thing what is given is the step angle. What is being asked is step angle. We already wrote an expression for the step angle, if you may recall. Step angle is whatever is the rotor pole pitch in degrees or radians minus stator pole pitch. So the rotor pole pitch, you can say, because it is 8 poles in the rotor, 360 degrees divided by 8 minus 360 degree divided by 10. 10 is the number of stator poles. So this is going to be 45 minus 36. So this is going to be 9 degrees. So 9 degrees happens to be the step angle. So step angle we have already solved for. The second one that is being asked, this is 1. And the second one that is being asked is what is the rotational speed? So if every phase is having 1 kilohertz pulse, that means 5 kilohertz is the frequency of pulses corresponding to all 5 phases. So if we are looking at all 5 phases, it is 5 kilohertz. And one pulse will give a movement of 9 degrees. So for one rotation or 360 degrees, we will have 360 divided by 9 degrees, that is 40 pulses. So if I have 40 pulses, one rotation will be accomplished by the SRM or by the stepper motor. So I can say 5000 is the frequency, 5 kilohertz or 5000 pulses are given for 1 second divided by 40. That will give me exactly the rotation per second. So the revolution per second is 500 divided by 4, which is 125 revolutions per second. Or I can say 125 multiplied by 60 revolutions per minute. So this corresponds to 7,500 RPM. So the kind of speed what we get in the stepper motor, if we assume we are giving 5 kilohertz pulse for all the five phases and we are not missing any pulses, it will be 7,500 RPM. Okay. And the last question what is being asked in this problem is, if the rotational speed needed is 12,000 RPM, then what should be the frequency of pulses in each phase? So we can say, we can solve for this directly by saying 12,000 divided by 7,500. If I want 7,500, I will need 5 kilohertz. If I want 12,000, what is the frequency? So I can calculate like this. Okay. And this corresponds to 1.6 multiplied by 5. That is, we are getting actually this to be 9 kilohertz. So 9 kilohertz corresponds to all 5 phases. So 9 or 8 kilohertz, I suppose. This is actually 5 and this is 7.5. So we will get 8 kilohertz. This will correspond to 8 kilohertz. So 8 divided by 5, which is actually 1.6 kilohertz. So 1.6 kilohertz per phase. The frequency of pulses corresponding to every phase will be 1.6 kilohertz. You can definitely calculate whether it is coming out properly, because 1.6 kilohertz per phase is 8,000, 16 fives are 80. So that is going to be 8 kilohertz. So 8 kilohertz corresponds to, we already said that 40 hertz. We said 40 pulses correspond to one rotation. So 8,000 divided by 40 will give me 200 revolutions per second, which actually corresponds to 12,000 RPM. So if we want 12,000 RPM, the frequency corresponding to every phase has to be 1.6 kilohertz. That is inferred. Okay. So let me try to work out one more problem, one more numerical example on SRM. So the problem statement is somewhat as follows. Of 8 by 6 SRM operates with 1 kilohertz pulse train in each of its phases. Each of its phases. Calculate the speed of rotation, assuming that no pulses missed. This is the first subdivision. The second subdivision is if the inertia of the motor load system is 0.02 kg meter square, and if the load torque demand is 2 Newton meter, and if the phase inductance varies from 10 millihenry to 120 millihenry within a span of 15 degrees variation in rotor position, what should be the current carried by the stator winding so that the acceleration of the rotor is from 0 to 1500 RPM within 3 seconds. So what is given is the minimum inductance, the maximum inductance, the variation within what span, the load torque demand, the inertia, and the acceleration required. For this, what is being asked is the current. Okay, so this is what is being asked. Now let us try to solve the problem. The first subdivision is straightforward. What is given is 8/6 SRM, so it is actually a 4-phase SRM. So we are going to have A dash, B dash, C dash, and D dash as the 4-phase windings. And each of them is going to have 1 kilohertz train of pulse. So the overall train of pulse corresponds to 4 kilohertz. 4 kilohertz is the frequency of pulses when all 4 phases are put together. Okay. Now, we have to calculate what is the kind of 8/6 SRM. I can calculate what is the step angle. Step angle is going to be 360 divided by 6 minus 360 divided by 8. So that is going to be 60 minus 45, which is going to be 15 degrees. So step angle is 15 degrees. So for one rotation, we can calculate how many pulses are needed. So that is going to be 360 degrees divided by 15 degrees. So that is going to be 24 pulses. 24 pulses are needed for one rotation. Okay. So if we say 4,000 are the pulses per second. 4,000 divided by 24 will be the revolution per second, or 4,020 divided by 24 multiplied by 60 is going to be revolutions per minute. So this is going to be RPM. So I can say this corresponds to 4, and so this is going to be essentially 10,000 RPM. The revolution per minute is going to be 10,000. So the speed in RPM is going to be 10,000 as per this. If I'm going to give 4 kilohertz being the frequency of the pulses corresponding to all 4 phases, we will have the speed to be now 10,000 RPM. Okay, so this solves the first subdivision. The second subdivision, let us try to work out. So we can say inertia is 0.02 kg meter square. This is what is J. D omega by dt we have to calculate. So d omega by dt is 1500 RPM within 3 seconds. So 1500 RPM we can calculate in terms of radians per second. 1500 multiplied by 2 pi divided by 60 divided by 3. So that is essentially, if we calculate this, this is d omega by dt in radians per second square. Okay. Now, J d omega by dt is the torque requirement for acceleration. So this is accelerating torque. So this is essentially 0.02 divided by 3 multiplied by 1500 multiplied by 2 pi divided by 60. So this comes out to be 1.0467 Newton meter. Now we know that J d omega divided by dt is equal to Te minus TL. So what is the electromagnetic torque to be generated by the switch reluctance motor? That will be equal to J d omega divided by dt plus TL. So that comes out to be, TL is already given as 2 Newton meter. So I can add the 2 Newton meter to this. The total will be 3.0467 Newton meter. This is what is TE. And we derived the expression in the previous slide, saying that half I square dl by d theta multiplied by is T. We derived this expression, if you may recall. So let us say half times I square multiplied by dl by d theta has to be now 3.0467 Newton meter. We have to first calculate what is dl divided by d theta. dl by d theta, the inductance is varying between 10 millihenry to 120 millihenry within a span of 15 degrees. So that is going to be 120 minus 10 multiplied by 10 power minus 3. This is the Henry. And theta is 15 degrees. That has to be converted into radians. So 15 degrees multiplied by pi divided by 180. Okay. So this is going to be actually our radians. So this is coming out to be 0.4202 Henry per radians. So substituting this dl by d theta here, and I can calculate I square equal to 3.0467 divided by 0.4202 multiplied by 2. This is what is I square, from which I can calculate I to be 3.81 ampere. So the average current that needs to be pumped in through my phase winding of the SRM is 3.81 ampere as per this particular calculation. One thing you have to remember is it's not very easy to pump in this average current because the inductance is first of all varying. If I know even the resistance, it's not very easy to calculate what kind of voltage I should be applying to my SRM winding. So that is one reason why SRM control becomes very, very difficult. One is the inductance itself is varying, and because of saturation, what happens? The inductance need not be a linear variation. We drew the inductance variation somewhat as linear, when we calculated the SRM current and when we inferred the electromagnetic torque. So this linear variation is assuming that I am not really having any saturation. When I have saturation, the inductance itself is not going to follow a linear profile. That is one reason why SRM control has really become a fertile area of research. In fact, if I want to have sensorless control of SRM, if I want not to have, I do not want to have rotor position sensor included in the SRM drive. In that case, what I need to do is, if I know what is the voltage that is being applied, and if I know the resistance of the winding, I can try to get what is VDC minus IR. That will actually give me what is d of Li divided by dt. Now, this is essentially what is the change in flux linkage. Now, this change in flux linkage, if I try to integrate over time, or if I say VDC minus IR multiplied by whatever is my delta T, that is, if I sample the current and sample the voltage over a period of time, delta T, and then if I try to multiply VDC minus IR by delta T, then I would get what is delta psi or variation in the flux linkage. And if I know what was the old value of flux linkage, and if I add this delta psi to that, I will get what is psi nu. Now, if I know this psi nu, and if I divide this by I should be able to get what is L value at this particular moment. And if I know originally L versus theta characteristics stored as a lookup table, then I should be able to know what is theta. So from L nu, if I have L, I, theta kind of lookup table already stored, I should be able to get what is theta, and this gives me the rotor position information. And if I have the rotor position information, I don't really need, no need for a rotor position sensor. So when I don't need a rotor position sensor, I call that as the sensorless control of SRM. I would be able to tell about this as sensorless control of SRM. So for sensorless control of SRM, what I need is a voltage sensor and a current sensor. I should know the original value of resistance, and using that I can integrate VDC minus IR, and I would be able to arrive at the flux linkage, and flux linkage divided by the current, I would be able to get what is my inductance. And if I know inductance, and if I have already stored the information based on the geometry or by based on some measurement already I have done for the SRM, I will have L versus I versus theta lookup table from which I will be able to get the rotor position information. So this will allow me to implement sensorless control of switch reluctance machine. Okay. So in the next class, we will be looking at PMBLDC motor functioning and its control aspects as well.